Thank you for introduction. And as you already mentioned, I'm Doyeon Kim, and currently I'm working at Line. And I started this research when I was a master's student, and I wrote the smart contract fuzzing technique with only dynamic data flow analysis in my master's thesis. And I joined Line right after graduation with master's degree, and I still kept researching into smart contract fuzzing with other research members. Yet this is joint work with my colleagues, Jason, Sumin, Gustavo, Alex, and lastly, my advisor, Sang-gil Cha. And we published the paper at Automatic Software Engineering Conference, which is one of the top tier conferences in the software engineering field. Also, we open sourced Smartian, which is a gray box concrete fuzzer with static and dynamic data flow analysis for finding bugs in smart contract. So today's topic is same with it. So if you are more interested in the topic after listening my presentation, you can read our paper and see our open sourced project named Smartian. So I will start to introduce the basic concept of smart contracts. So our research specifically targets Ethereum smart contract, which is the popular smart contract platform based on blockchain. With the growing popularity of blockchain and smart contract, I think everyone knows the blockchain and smart contract. In short, blockchain can be thought as distributed computing system, and a smart contract is a collection of data and code which is located in the blockchain. So smart contract can perform various operations. So one of the important operations of smart contract is related with digital cash called Ether. So for example, a contract may transfer Ether to other contract on the blockchain. And smart contract is executed on EVM. It stands for Ethereum Virtual Machine. So next, I will introduce some characteristics of a smart contract. In general, the contract code defines a set of functions and provide them to the users. Each of the function can read or write state variables of the contract, which is similar with global variable of a C program. In other words, this variable persists after the execution of function. So when we call function f here, it will update the state variable. And later, when we call function g, we will use the updated value of the variable. Such state variables are useful for holding the data of the contract. For example, let's assume there is a smart contract that runs a bank, and then this bank contract can store the balance of each customers in a state variable. And the customers will deposit or withdraw their money by calling the contracts function. Because smart contracts deal with digital assets, a bug in smart contracts can cause a catastrophic loss. Indeed, there have been famous exploits on Ethereum smart contracts, such as re-entrancy attack on a contract called DAO. This attack had stolen a tremendous amount of Ether, which was worth $70 million at the time of attack. So this highlights the importance of testing smart contracts. So there are lots of techniques for finding bugs. One of the most popular techniques is static analysis. So static analysis approximates the program behaviors without actual execution. So we can guess how to execute the program before it runs. Through this approximation technique, we can investigate various semantic properties during program execution. For example, we can guess whether buffer overflow bug is occurred or not. More specifically, we can predict which access to array can trigger buffer overflow before the program execution. So static analysis is that it doesn't execute target program, so we can predict whether there is a bug or not. On the opposite side, there is fuzz testing. It is usually called fuzzing. Fuzzing is a process to execute the target program repeatedly while randomly change the input of program. So we expect that the program occurs some critical errors like crash. So although the fundamentals are really simple, fuzzing is gradually advanced in various aspects. It has become an effective technique for finding program vulnerabilities. And many software companies such as Google and Microsoft use fuzzing a lot. The stateful property of smart contract brings an interesting challenge. In smart contract fuzzing, a test case is a sequence of transactions, which is function calls. So therefore, deciding the order of function call is a critical problem in smart contract fuzzing. So let's consider this example code where we can trigger the bug in function G by setting the state variable into a specific magic value from function f. Now, if we have a sequence that calls f before g, we have a chance to trigger the bug by mutating the argument of f. In contrast, for a sequence that calls g first, we cannot trigger the bug though we mutate the argument. Here, g will always use the initial value of the state variable, which is 0. Because g uses the state variables before we update its value. So I'd like to note that the traditional coverage-based fuzzing is not effective in recognizing which sequence is meaningful or not. This is because these two sequences, or the two test cases, achieve the same coverage. In other words, if we already have the second sequence in our test case pool, then the first sequence will be considered as an uninteresting one because it does not bring any coverage gain. So previous work has proceeded several techniques to handle this problem. For example, one of the previous work used to machine learning to decide which sequence order is more promising and meaningful. So let's take a look closer. This example is different with one in the previous slide. If S1, that means seed 1, is an initial seed, we can cover line 3 for function argument mutation like S1 prime. And one more mutation finally makes S bug, which triggers a bug. See that S1 prime covers line 3. Then let's think that there is S2, which is an initial seed that executes F and H orderly. we can get S2 prime using mutation. And S2 prime also covers line 3. And let's assume that if a seed pool includes these seeds in the dotted line, and let's assume that S1 prime appears next, then the traditional code coverage-based fuzzing doesn't think that S1 prime is not meaningful sequence because it doesn't cover new line because S2 prime already covered line 3. But you know that S1 prime only trigger the bug. That means the traditional code coverage-based fuzzing missed its opportunity to trigger the bug. So in our paper, we mainly do fuzzing for finding bugs in smart contract. But how to fuzz efficiently? For that, we propose a novel approach based on static analysis, which we believe to be complementary to the fuzzing. First, we statically analyze the target contract code and identify the data flows that can occur between the functions. Based on this, we decide which function call sequence is expected to produce such data flows. Then we initialize the fuzzing seeds with those promising sequence and pass them to the fuzzer. So the summary is we integrated static analysis with fuzzing. That means static analysis collects program knowledge so that it can improve fuzzing performance. So before providing more technical details, I'd like to present the overall architecture of our system, Smartian. At a high level, Smartian takes in target contract code and outputs the bug found by fuzzing. First, the static analysis module will identify possible data flows and initialize the seeds by considering these data flows. Then the generated seeds are passed to the fuzzing module. When the fuzzing module starts to run, this time we employ dynamic data flow analysis to improve the effectiveness of fuzzing. I will cover more technical details of each module one by one. So, first, let's take a look closer at the static analysis module. Generally, the contract code is first written in high-level language, but it eventually has to be compiled into a low-level bytecode. And our system receives the contract in the form of bytecode. Therefore, the static analysis for data flow is not trivial because we have to observe the low level by instructions. Some people wonder why we use binary, not source code. The main reason is smart contracts are deployed to the blockchain in bytecode form. So there is a high probability that the source code does not exist. And someone may intentionally not provide the source code of smart contract. Due to these reasons, it's easier to get bytecode than source code. So we aim to enable fuzzing, even if source code is not possible, not available. Anyway, first of all, I have covered static analysis module of our system. Now let's proceed to do static analysis, which starts running with provide initial seed pool. So from now on, I will present more details about our static analysis. The smart contract bytecode runs in a virtual machine called EVM. And EVM is a stack-based machine, and it comprises 3 components. First, the stack is used to hold the operands of every instruction. Second, there is a memory, which is an address to byte mapping. Lastly, the persistent storage is used to maintain the state variables. Now, let's assume we have this bytecode that accesses state variables. What we have to do is figuring out which operands are used by the instructions that access the storage, such as the sload instructions in this bytecode. For this, we analyze the semantics of every instruction and trace how the stack and memory change along the execution. In the end, we can find out which operand is on the stack when the sload instruction is executed. And this instruction will use its operand as the storage address to access. So that was the low-level sketch of our static analysis, and now let's summarize our static analysis at a high level. For each function, we run a flow-sensitive analysis and approximate the execution state of EVM at every program input, every program point. Based on this, we can identify which state variables are loaded and stored by the analyzed function using sload and store instructions. Now we have to generate the initial seed pool for fuzzing by utilizing the static analysis result. And I will show you the formal algorithm for seed initialization, which is present in our paper. But before I show you, I will explain the high-level idea first. So first, we identify the function call orders that may produce data flows across the functions. Then for each of the identified order, we ensure that there is at least one seed that includes this order in the sequence. Yeah, so this is high-level explanation for seed initialization. So before I explain in detail, we need to know about the variables used in seed initialization algorithm. The seed initialization algorithm takes 3 inputs. One is funcs, which is a set of identified functions. Next is defs, which is a map from each identified function to the state variables defined by the function. And the next is use, which is a map from each identified function to the state variables used by function. So all the information is obtained from static analysis about which I already talked. So we can guess defs using store instruction and use using sload. Also, there is other variable used in seed initialization algorithm, which is data flow gain. It is a function level data flows as triple F1, V, and F2 from a given sequence, where F1 and F2 are functions that appear in the sequence, and second, F1 defines V and F2 use that V. So this is the formal algorithm for seed initialization. it takes in as input function defined one and used one. In line 3, we initialize the work list with singleton sequence containing each function in funcs. We ignore functions that do not define any state variables as they cannot affect the persistent state. Next, we pull a sequence out of the work list and create new sequences by appending each functions in funcs to S. So we then examine each of the generated sequence with data flow gain to decide which sequence covers previously unseen data flow. Line 9 pushes such sequence to the work list and internally removes redundant entries for greater efficiency. We repeated extend sequence in the work list as long as a new data flow is observed. If a sequence produces no gain by extending it, we finalize the sequence by adding it to the output set. So far, I have covered the static analysis module of our system. Now let's proceed to the fuzzing module of Smartian, which starts running with the provided initialization seed pool. So even though the seeds are initialized with meaningful sequence, we still have to mutate these initial seeds to realize the expected data flows. For example, let's consider this contract where function f updates a state variable and function g uses it. So we have to call f with 41 and 61 and to trigger the bug at line 7. And our static analysis module will initialize the seed with a promising sequence, F and G orderly. But the fuzzer still has to mutate this initial seed to obtain the bug triggering seed. During this process, the fuzzer will first find an intermediate seed like S1'. It is important to recognize this intermediate seed as an interesting one and add it to the evolving seed pool. For this, we dynamically analyze the concrete data flows that occur at runtime and use them as feedback to evaluate each seed. So in this example, S1' realized the data flow from line 3 to line 6, which is not present in S1. Therefore, we can consider S1' as an interesting seed and add it to the seed pool. Later, it will be selected and mutated again, and we will have a chance to find the bug triggering input. Now, it is bug oracle for fuzzing, which is one of the important parts. In traditional binary, it is quite simple to recognize which one is bug or not. But unlike traditional binary, smart contract bugs most do not incur a crash. So we must implement bug oracle that monitors the execution. So Smartian implements bug oracles for 13 classes of bugs, and we investigate previous works on finding bugs from smart contract. And first is assertion failure. It occurs when the condition of an assertion, assert statement is not satisfied. So finding such a bug, we check if an invalid instruction is executed. And next one is arbitrary write. So it is occurred when an attacker can overwrite arbitrary storage data by accessing a mismanaged array object. And we checked if someone accessed storage data in location that is larger than the length of storage, and its bug oracle is same with Harvey. And the next one is requirement violation. And it occurs when the condition of a required statement is not satisfied. And we check if a revert instruction is executed. But you might think it's weird because assertion failure and requirement violation can occur frequently. Indeed, actually, requirement violation is not kind of bugs. So we also thought about that, but we just followed SWC registry, which is smart contract weakness classification, and some tools already implemented such bugs. So comparing with other tools, we added such bugs. So when you use Smartian, we turn off assertion failure and requirement violation on default mode. And next one is block state dependency. This occurs when block states such as timestamp and number can decide either transfer of a contract. So we check if a block state such as timestamp and number can affect on either transfer, tracing both direct and indirect flows for this. Next is control flow hijack. It occurs when an attacker can arbitrarily control the destination of a jump or delegate call instruction. So we raise an alarm if someone can set the destination contract of delegate call into an arbitrary user contract. And also it reports an alarm if the destination of a jump instruction is manipulatable. So somebody already knew that delegate call is already deprecated, but some developers still use old compiler version which delegate call is not deprecated. So we considered this kind of bugs. So next is either leak. It occurs when a contract allows an arbitrary user to freely retrieve either from the contract. So we check if a normal user can gain either by sending transaction to the contract only when the transaction sequence does not have any preceding transaction from the deployer. Actually, we solved this issue very heuristically, but we saw lots of smart contracts which deployer is mostly an owner of smart contract. And the owner usually has a permission to transfer either to someone. So if there is a case where the deployer sees a transaction during sends a transaction during a sequence and anyone can get either, this situation is excluded as bugs because the deployer might allow it with a high probability. So in despite of our tries, there can be false positives. So next is freezing either, which is a contract can receive either, but does not have any means to send out either. So we check if there is no way to transfer either to someone during the execution while contract balance is greater than 0. And it's it is same bug oracle with contract fuzzer. And next one is mishandled exception, and it is about a contract does not check for an exception when calling external functions or sending either. And we taint the return value of call instruction flows into a predicate of a jump I instruction. And if there is a return value that is not used by jump I, then we report an alarm. And next one is multiple send. So contract sends out either multiple times within one transaction, and this is a specific case of those. According to SWC registry, it is dangerous such case, so we detected. So next one is integer bug, and everyone knows about that, but yeah, integer overflows or underflows occur, and the result becomes an unexpected value. So we check if the overflow or underflow value is used to the critical values, variables, yeah. And next one is reentrancy. It is a function in a victim. It is a function in a victim contract is re-entered and leads to a race condition on state variables. So we monitor if there is a cyclic call chain during an either transfer, then use taint analysis to identify state variables that affect this either transfer. And finally, we report if such variables are updated after the transfer takes place. So next is suicidal contract, and it is occurred when an arbitrary user can destroy a victim contract by running a self-destruct instruction. So we check if a normal user can execute self-destruct instruction and destroy the contract, and we filter that have any preceding transaction from the deployer in the sequence. It is same case with either leak. And the last one is transaction origin use. It is occurred when a contract relies on the origin of a transaction for user authentication. So we taint the return value of origin instruction and check if it flows into the predicate of a jump I instruction. Also, it is already deprecated as well as delegate call instruction. But with the same reason, we implemented this bug oracle. So next is implementation, and I will briefly summarize the implementation of Smartian. For the static analysis module, we used B2R2 as a front end and wrote the main analysis logic in 1,000 lines of F# code. And for the fuzzing module, we used Eclipser, which was originally designed for Linux binaries and extended it to support smart contract bytecode. Also, we used the EVA implementation from Nethermind to emulate the execution of the bytecode. And we implemented dynamic data flow analysis on the top of it. So now I will present the evaluation result of Smartian. In this talk, I will cover the two evaluation questions. For the remaining evaluation question, please refer to my paper. And first, we studied whether our static and dynamic analysis indeed improve the effectiveness of fuzzing. And second one is we studied whether Smartian can outperform other testing tools. So, to answer these two evaluation questions, we used two benchmarks from previous work. For the comparison purpose, we chose two fuzzers, and 2 symbolic executors for smart contracts. And we ran our experiments in a Docker environment to ease their reproduction. So first, we used the benchmark from very smart paper to evaluate the impact of our data flow analysis. Because Very Smart is not a testing tool, it is not our comparison target. Still, we found this benchmark valuable because it's composed of real-world contracts that have non-CVEs for integer overflow bugs. The graph plots how many CVEs are found over time, and it compares 3 different modes of Smartian. The first mode runs without any data flow analysis, and the second mode runs only with static data flow analysis. And lastly, the third one runs with both static and dynamic data flow analysis, and this is the default mode of Smartian. And the graph shows that Smartian can find bugs more effectively when both of the analyses are enabled. So someone wants to know the result with dynamic analysis only. So I already experimented it. Compared to the static analysis only, the performance was slightly lower in the case of only dynamic analysis. But when with static and dynamic analysis, it performs is the best. And next, we compared Smartian against other testing tools. We used the same benchmark here, but there were contracts that some of the tools failed to properly run. Those we excluded these contracts for fairness and then compared Smartian against other tools. The result indicates that Smartian found at least 2 times more CVEs than other tools. We note that one of our comparison targets, IRF, is missing here because it does not support integer overflow detection. Therefore, we ran additional experiments for the comparison. So we constructed the second data set by extracting contracts from Smartbugs, which is a benchmark with labeled bugs. So they are various classes of bugs in the label, and we collected contracts that have these 3 bug classes because these bugs are supported by all of tools we tested. Again, Smartian found the largest number of labeled bugs, although the gap between Smartian and Mithril is smaller this time. One possible reason is that this benchmark contains not only real-world contracts but also artificially made toy contracts where triggering bug is relatively easier. So due to the limitation time, I cannot present all the details of Smartian. Therefore, please refer to our paper if you are interested in the design details of our system or the result of more thorough evaluation. So we believe there are lots of several interesting directions for future work. And to support open science and foster future research, we make Smartian available at GitHub. Also, we release the artifacts for evaluation so that our work can be reproduced easily. So if you are interested in our work, please visit our repository and try Smartian. So this is the end of my work, and thank you for listening.